So where are we? This other, in the first section, for some reason I had fallen a little bit behind, so I'm losing track of in each section where we are. We finished periodic.
We did an example.
We did an example,
Cam.
so we finished that,
Yeah.
right? So that means, okay, now we can summarize and see where we are. So let me do this then. So let's summarize this. Okay. What basically we have done in the course, because the topic we're just about to cover really brings the whole topic of single degree of freedom systems to a closure. So let's see where we are, what we have done. We studied with free vibration. Okay. Free vibration. We looked at, of course, both undamped and damped systems. Okay. For the undamped system, it was a harmonic, basically, response, and same thing here, but the harmonic response had some phase shift with respect but anyway, we're not going to go to the details of it, just what we have done so far. Then we got into forced vibration. In the forced vibration, what we have discussed is harmonic forces, and we look at both undamped and damped systems, right? And especially in this case, with damped system, we really explore that and discuss all these topics such as rotating unbalance and so on. So the next topic, which was a sort of a subcategory of harmonic forces, was periodic forces, which basically is similar to harmonic, because we learned how using Fourier series, you can convert any periodic force to a series summation of harmonic functions, right? Now what we are going to study for actually several sessions would be general forcing function. As you can imagine, this is really a concept that is much broader than this special case, because what we are talking about is that we are going to look at the response of a single degree of freedom system under the action of any loads, no limitation, no restriction whatsoever. This loading function can be an impulse load, can be an impact load, can be a blast load, can be earthquake load, you name it, any kind of loading, wind load, depending on the systems that you have. So basically what we are saying is that we are going to look at the response of the mass under the action of a general function. Okay, so that's what we're going to study now. This is, of course, as I said, is a general concept. It's not an easy topic, I have to admit. The approach to derive the response is done in two different ways. One, by using a concept, which of course you haven't had that probably in your calculus or mathematics that you've studied, is convolution theorem, which we are obviously going to avoid that. The second approach is Duhamel integral, which reaches actually the same results using a different approach, which is based on physics, okay? Mr. Duhamel deserves the credit for that. I think he was German, if I'm not mistaken. But anyway, so that's one thing I like about this book of Rao. I guess at the beginning of each chapter introduces all these eminent people who have contributed to those concepts. And I think he talks about Duhamel too. But anyway, so what do we have here? In other words, how do we approach the problem? First of all, we know that the foundation based on which the whole course is laid on is that we assume this is a linear system. So when you have a linear system, what does that mean? That means if you have several forces or loads acting on a system, if you find a response of that system under the action of each individual load and add them up, that'll give you the total response. And that's general, not related to vibration, right? You have in the strength of materials, for instance, right? You have a beam, you want to find, for instance, you know, the moment diagram under the action of these three loads, right? So what you can do, you can think of this as being basically a summation of these three cases. So if you find the moment diagram for this case, and this case, add them up, would be the moment diagram under the action of all of these. All of this is because the system is linear, so as long as you have a linear system, that is the material is within this range, right? Obviously, due to that linear function, the responses just add up, okay? So that's the basic concept behind Duhamel integral that we are going to use. And what is that? Let's do this. Instead of looking at this function as is, I would think of it this way, that this function is made of an infinite number of loads like this, okay? In other words, you break this down to infinite number of loads that you would say, these are each, okay, loads applied at a certain time with certain duration, okay? So if I find a response of this system under this load, okay, which is applied at any arbitrary point, okay, and this response at every single one of these throughout this entire period that the load is applied, I can find the total solution. In order to do that, let's introduce a few terminologies, okay? First of all, a loading like this that is applied with a short duration, we call that an impulse loading. So impulse loading is a load with short duration. Okay. Impulse itself is the magnitude of that force times the duration that is applied. That's called impulse. Now let's go back to some basic physics. You may or may not remember, but at least you could remember the concept of momentum from physics, right? An impulse applied to a system. And I put that actually F sub I. I can even put F like this, but for the simplicity, for the time being, I'm just gonna use this notation, F d tau. An impulse applied to a system causes a change in the momentum, okay? Change in the momentum, which is written like this, or we can write it as this, okay? Since mass is assumed to be constant, you can take that out, so this can be written as this. Depending on whatever forms you write that, doesn't matter. But if you write it, for instance, like this, take the mass out, you can write F as being d over d t of m u dot, or I'm sorry, d tau. Okay. Anyway, this force causes a change in the momentum, and what does that mean? If I write this, okay, in a different way, as I had before, you know, like this, d tau over m is equal to d dt, okay, of d u, okay? So I just write that like that. You can see that clearly that an impulse does what? An impulse causes a change in the velocity. Okay? In other words, when you apply an impulse to the system, which even is intuitively obvious if you have a system address, right? For the lack of a better analogy, just throw a big rock to this chair, right? What does it cause? This poor chair was sitting at rest, no displacement whatsoever. All of a sudden, is subjected to a change in this velocity, causes initial velocity. In other words, the action of an impulse on the system is this. If you think of initial conditions, that initial displacement is 0, but you have an initial velocity, which would be f d tau over m. In fact, this concept is the general form of the second law of mechanics. And you can see that I'm intentionally avoiding the name Newton. Second law of mechanics, right? What does that law says? It says rate of change, okay, rate of change of momentum of a mass is equal to the force acting on it. Okay, which is basically this, which is same as F is equal to ma, but the most general form, because the general form is better because it considers a possibility that even the mass can be a time-dependent quantity. So this is really this is the most general form of the second law. But we don't care about that. All we want, or all we conclude then, is that so the problem now can be looked at this way, that we don't have basically a force vibration. We have a system which was at rest, and due to this impulse, it is subjected to an initial velocity, right? So what does that mean? That you have basically a free vibration due to initial conditions. And we had that, right? We had the solution. If you remember, going back to your notes, what was the solution? In other words, let me redraw that because it's very important. So what we are saying is you have a force right here of this magnitude, this duration, this impulse load, applied at this time of t is equal to tau. So right there, this force is going to generate a displacement, and that displacement was what? It's a free vibration due to that initial condition being just the initial velocity. in general, this was the form. If you had a damped system, the steady state response of that system due to initial conditions was this form. If you go back to your note, you will find that way back. Okay, this was U dot plus sine omega d t divided by omega d U dot. This was the general form. In other words, the response right there, due to the action of this impulse, results in a motion, that the steady state motion that can be described like that. But here, we said that the initial displacement is 0, right? We only have initial velocity, which is that F d tau over m. So let's rewrite this, and I would just take those common terms out. So basically, this would be what? This would be F d tau over m times, I'm just rewriting it in reorder that, arranging the order. Okay. Okay. That would be what? I would write it like that. Yeah. F day tau, okay, minus t, okay, sine of omega d t. So I just rewrote this in a different way. So this is the initial velocity, that and so on. Okay. But what is this? This is the response of the system right at that moment when the initial velocity is applied, right? But that's not what we are interested in. We want to look at the response of the system at any point here, where this is t, okay? We want to look at the response at any point t minus that moment that this impulse was applied. So this is what we are interested in. We want to find the response at that particular point, okay? Which is a general point, obviously, right? So therefore, the response at that point would be what? The response at the time t minus tau after this. So what would that be? That would be just that. The response then at that point would be f d tau m 1 over omega d e minus zeta n t minus tau sine omega d t minus tau. So let's summarize that. If you have an impulse that acts on the system at this time, after this impulse is applied to the system, at any point, which is t minus tau, away from the moment of the application of this impulse, that would be the response of the system. But what about this now? We said that this is the response of the system to one of these impulses, right? This can happen anywhere from all the way here to here. So how about if I want to add up the response due to the action of all these all these impulses? What that means, the total response would be the integral from 0 all the way to any arbitrary time t, okay, of this. Okay, so I will take basically 1 over m out, or 1 over m omega d, which are the constants out. So I will just have f of tau, okay, e to the minus zeta omega n t minus tau sine omega d t minus tau, okay, d tau. This is called Duhamel integral. In other words, in order to find the response of a system, this is what it means. If you have a forcing function, f of t, in order to find the response of the system under the action of this force, you perform an integration, which is called convolution integral or Duhamel integral, that mathematically what you do, you consider integrating in time of functions that are in terms of this dummy variable tau. That's what mathematically you're doing. Okay. It may sound very complicated, it may sound too physics-y or physics-based stuff, but let's show actually the powerful application. Step by step, I want to do a good number of problems to demonstrate the application of this concept, okay? So let's see. Okay. And the first one that I will do is this. Is something that is, you've already seen that without knowing that that result was based on derivation that were based on Duhamel integral. This is what I'm going to do. Let's consider a simple case. You have an undamped system, so that's its most general form. That was the damped case. So if you have an undamped case, obviously this becomes omega n. This becomes also omega n. So, and obviously this is going to become 1, right? In the case of basic damping 0, this would be just simply 1. So you have just those terms. So this is the most general form. So I'm going to just consider a special case now, which you've had it in design, in Shigley, and all those places. Let's say you have a system, as a structure, a mechanical system, that is subjected to an impact load. Impact load is described like this. This is the table. I just throw a heavy rock, drop it on this, sits on it, and causes some vibration, right? So, in other words, a system that at time 0, there was no load on it, but at time 0 and afterward, a constant load acts on the system. Impact is different from blast load, okay? So magnitude of this I call F bar. So we want to find the maximum response, okay? Or the maximum displacement due to this load. You've seen in Shigley or whatever design book that for the impact load in the design, you use the factor of, what is it you called it? I don't know, dynamic factor or design factor of 2, right? Remember that. So let's see where that came from. And that's what we're going to do. So basically you have a forcing function that is 0 when time is less than or equal to 0, and it is a constant value when t is greater than 0, okay? initial velocities, of course, are given. What we have then, the general response, okay, would be what? As I said, would be a special case of that. You will have F tau, which I'll just write the general form first. If for the undamped case, this becomes 1 over m omega n from 0 to t of F tau, okay, sine omega n t minus tau d tau. That's, which is much simpler, okay? But this is what you have for that f of tau after t is equal to 0. So if you substitute that in there, you just have f0 over m omega n, the integral from 0 to t of sine omega n t minus tau d tau. So in order to perform this integration, obviously, you need to break this into sine omega and t cosine tau minus, in other words, the trig identity, okay? So if you do that and take the integration, you get f0 over m omega n times 1 over omega n cosine of omega n t minus tau d tau, integrating it from 0 to t. Always integrate that with, in that range to find the time response. So what you find is f0 over m omega n times 1 minus cosine omega n t. Okay. Oh, actually, f omega n squared, I'm sorry. Or, in other words, if you substitute for omega n squared, you get f0 over k times 1 minus cosine omega n t, right? This is u. Okay? So what does that mean? That means this is the static displacement, isn't it? This is the usual thing that we've had, right? So what does that mean? That means the maximum response of this system under the action of this constant load, right, would be when? Would be when this function is a maximum, right? So what is the maximum value of cosine omega t, or cosine function? Is either negative 1 or right, or 1, right? So the maximum value occurs, maximum value of this quantity occurs when what? You have 2, right? That would be 2. So maximum displacement would be 2 times f0 over k, or it's twice the static response. And that's where that dynamic factor 2 comes from. We call this dynamic load, or dynamic load factor. That's why for an impact load, we always consider a factor of 2 for the dynamic load. And that's where it comes from. Okay. So that's, I'm going to, although I had another example here, in all fairness to the first class, maybe I will just stop here, because they're a little bit behind. We just started this. So I'm going to stop here, and there's no class on Friday. We are already ahead of the schedule by 1 or 2 days anyway. So hopefully you can enjoy that Friday and finish your projects, yes.
Wasn't the example?
I'm sorry? Oh, it's called dynamic factor.
No,
Dynamic
he anyways.
factor,
Oh, yeah, that should be.
Okay.
or dynamic load factor.